enthalpy split. Remember, we were talking about a sensible temperature split. We're talking about our 20-degree split. We're talking about the 12-degree when it's humid. That's talking about sensible cooling. That's how much cooling you can do on the sensible side. Then the latent side kind of creeps in there and causes that sensible split to go down because more capacity is needed on that latent side, getting that humidity out of the air. Now, enthalpy split, that's going to be talking about total heat. How much total heat changed from return to supply. How much cooling it took place, how much humidity was taken out of the air or water taken out of the air. They call it grains on a psychometric chart. And if you have a psychometric chart, which is a good idea, enthalpy is that reading that's on the slant on the left side of the chart over there, going all the way up the chart. Basically, you'll get your relative humidity and your sensible temperature, like you have 75 degrees, 50%, and you'll draw that diagonal line right up there to the chart, and that'll give you your enthalpy. My suggestion, because I can't draw on this particular picture right now, just didn't set it up to draw on it, which I should have probably, is get an app or get instrumentation that will measure enthalpy. You can get an app where you can put in the measurements you have. It'll give you the enthalpy, or you can just measure it with whatever instrumentation you have. That's the way I'd go because that's easier. And if you have one of these wonderful devices, these wireless devices that we all seem to have now, a lot of them will do that for you. So enthalpy split, it's very important because it takes into account both sides of cooling. Theoretically, it's going to be 6.7 when the airflow is correct. Now it's actually like 6.67. But if you have everything aligned perfectly, 6.7 is where it will be with 400 CFM per ton. That's our nominal CFM per ton that we all talk about. Usually it's like we have a 2-ton unit. It's going to be 800 CFM, 3 tons, 1200 CFM. Using that method, 400 CFM per ton, which may or may not be where you end up setting something, the enthalpy split should be 6.7. And if we keep going here, enthalpy split, when the CFM goes down, the enthalpy split will increase. Much like just a regular sensible split, if your CFM goes down, it will start getting larger. That more time it's exposed to the coil allows more heat to be taken out of the air. And where you might have like a 15-degree split, maybe you get a 17 or 18. Another good reason to have Measure Quick, it'll tell you when you're outside the perimeters and your airflow is too low because your split's too high. Enthalpy split is similar. It'll grow too. It's not as large of a number, but it'll get larger as the CFM goes down to a certain extent. So you'll notice the same thing between the two of them. Now we're doing air conditioning capacity. It's really pretty easy stuff. It's an easy equation here. The capacity is a CFM multiplied by delta H, which is the enthalpy split, times 4.5. So basically you measure your CFM. We did that when we first got there. We did that last show. Let's say, and I'll give you an example here in just a second. Actually, let's skip ahead to the example. CFM times delta H times 4.5. 4.5 is a constant. So let's not even worry about that. We don't even care why 4.5 is there. That's the constant. We just got to remember it. Equals our capacity. So if we plug in 800 CFM for a 2-ton system, we multiply it by 6.7, which is our theoretical enthalpy split, what it should be, and multiply by 4.5, you see it comes out as 2 tons, or 24,120 BTUs. That's why I say it would be like 6.67, because it puts you directly at 2 tons. Now, when you get into the real world here, you're going to notice that there'll be issues with the system. Bad ductwork, bad charge, blocked off airflow, all sorts of stuff. So the airflow may be lower. The enthalpy split may be lower if the system is low in charge. And they may vary quite a bit. And you may get a certain amount of sensible and latent to add up to this number. So this is the total number. It's 24,000. So you'll have a sensible and latent component to it. And you add those together, that's where you get your 24,000. This gives you the total. And it's very important because when you're looking at a system to say, is this thing working correctly? You need to know what capacity it is. First of all, you look on the nameplate. Everybody knows it's like a 036, say it's 3-ton unit. You can do this equation after taking these measurements and then say, okay, well, this 36,000 BTU units running at 21,000. So there's definitely a problem. So you get a clear view of there being a problem with the unit. All you have to do is punch in these things or have one of these fantastic devices that will do it for you. And a lot of them will do it, like Measure Quick. I think everybody ought to use something like that. Measure Quick is the best. Hook it up to your stuff. It integrates into so many things. It integrates into Yellow Jacket now, which is pretty cool because they're the sponsor of this show. So no one gets mad when I say that. I was going to say it anyway, so I'm glad no one gets mad. This is great. So let's take a look at another one. The enthalpy split being 2.5 because there's a low charge. The system can't do the amount of cooling it should do. So you have 800 CFM times 2.5 times 4.5. It equals 9,000. So it's way lower. And you can see kind of the effect of that lowering delta H. Remember, delta H is just enthalpy. Enthalpy, don't even worry about anything else, but just knowing that's total heat. That's all it is. It's the total amount of heat. That's it. Sensible plus latent equals enthalpy.